Okay, hello, and welcome back to Old School Coding, where we're still working on that 1990 8080 based microcomputer, which is being simulated in C99 using software engineering techniques from the late 80s and early 90s. So we have pulled together a bunch of the support chips, and we've got an 8080 simulation which does all the instructions. It doesn't do interrupts or DMA yet, but I think we can defer that for now. We'll get the rest of this working. I want to see some results. We have a decoder which provides for a shadow mechanism that automatically resets. And as of the last session, we now have a serial device which we can set up to talk to a terminal window, which looks like this. There's my TTY window, and I have already run one test on it just before we started to verify that I can type into the window and it gets to the simulation. The simulation can turn it around and echo it, and we get back to the window. So, character devices are working. So the next thing I need before I can start doing something interesting would be a block device. Now, in theory, I could be building one of the systems dating from the early 70s, which you really had no mass storage. So basically your storage was a paper tape. And that's a viable model. Basically, you start in your ROM monitor and you say, load a program from tape, and it will read the tape in and load the program and so on. And that works. And you can punch the tape and you can read the tape, and it's all up to the operator to pick out the right tape to feed you. Well, I don't think that's going to be a great model for me. I really want to swing right into modeling a diskette drive. And I'm going to actually set up a mass storage device, which is a little bit more complicated. So, let's see what I have here in mind. I'll bring up these character devices on the right there. It was really simple. You could either, you could send data, you could read data, you could ask whether it's ready to send or not, you could ask whether it's ready to read or not. And I reserved a couple of bytes in the control port for we're going to do something. I actually reserved numbers for disconnect, reconnect, and explicitly said I'm not defining behavior for the rest of the codes yet. None of this is hooked up. So right now, all we could do is put characters and get characters through the CDEV. Well, we want to do something similar here with BDEV. We don't actually have a ring. In fact, I am going to data and edge. Okay, we're going to need 8-bit registers in this device. We're going to need edges. So let's leave all those the way it is. So we have a name. Block device does the following. Read a block of data from storage to memory and write a block of data from memory to storage. To support this, we need many registers. So we need destination memory address, 2 bytes. And all of our communication through in here is through I/O ports. I'm wondering if maybe instead we should make some sort of descriptor, because we're going to have a whole bunch of stuff. We need a lot of data. Memory address. I'm going to leave it TBD for the moment whether these are separate I/O ports, if they're layout in memory. Which drive, which track, which sector. Okay, so this is enough for a floppy disk controller. And if we want the block device to be just one drive, we have which track and which sector. But I want to allow for more specific things. So I'm going to say track, aka cylinder. Okay, so we now have which head. No, let's call it track. So getting to the next sector involves waiting. Getting to the next head involves electronically switching which head we're reading. Getting to the next track involves seeking, which takes a lot more time. And I'm going to build in an idea of mounted disk. No, I'm not. Actually, let's keep it simple. Let's keep it simple. I can extend it later. Okay, so in theory, if we allowed faking out up to, say, 255 sectors by 255 tracks, actually, I think one of these starts at 0, one of them starts at 1. I think its sectors are 1 through n, and tracks start at track 0. So this would be 128 bytes per sector times 255 sectors per track times 256 tracks per drive. This would give us a total capacity of, what is that, a bit over 8 megabytes, a bit under 8 megabytes. Anyway, 8.3. Let's put it in hex. No, let's not. Okay. So this is essentially just short of 8 megabytes for a drive. Now, the biggest drive I worked with in that time period, thinking 8080 based machines. So the biggest drive I ever attached myself to a 8-bit machine was a 5 megabyte Winchester drive. And I remember having to do all sorts of shenanigans. Another thing we could do is reserve 2 bytes each for track and sector and memory address. If I end up wiring this down in address space stuff, it means that I would have to rewrite a lot of code if I did this wrong. I'm going to go to 2 bytes for all of these. And we're going to say log base 2 of sector size. So we can select our sectors to be any power of 2. So this would be, so in theory, we could have sector size of 1. We could also have sector size of 2 to the 256. But that would allow us to have larger sectors. No, let's keep it simple. So if all we have is a memory address and 2 bytes, track and sector in 1 byte each. And in fact, we could always transfers to from. So we are going to always transfer to and from the same buffer address because we are super duper simple. So our operation consists of writing the track number, writing the sector number, and hitting a button to go. Ports are as follows. Call this the track number port. This is the sector number port. Control port. We're going to say write 00 to read disk and FF to write disk. Okay, and status port. Currently TBD. Now, I could say that when we start a read or a write, it's going to take a while, and sometime in the future we're going to come back later and we'll be done. Don't think I'm going to do that. So what I'm going to say is this is read FF if controller busy 00 if ready for command. So we're going to pretend that we have this. So basically, if the controller's off doing something, it will say I'm busy. And when it's done, it's going to go back to 0. So if you want to do a command, you've got to wait for it to be ready, and then you've got to issue the command. And if you want to have the data, if you want to read the data out of the buffer, or if you want to update the buffer for anything else, you've got to wait for it to go back to 0. Okay? So we're going to have that. That means that later on we could change the implementation to actually do that. I'm thinking maybe we will set it up so that the first couple of times you read it, it'll say busy, and then it'll go back to ready. That's not actually a bad idea. We could simulate the time by basically when you read from the status port, we could decide whether we're done or not. If we want to be really scummy, we could work out exactly when we start writing data and in what order the bytes appear and how often and when they appear. We could do all sorts of fancy things. We could do that all behind the scenes. So bdev, it's got an init and a linked. Oh, we need to have read and write. We need 3 ports. And this is track and sec. We are not allowing the DMA address to be set. That's going to play hob with CPM, isn't it? I think I'm going to do. I'm going to support multiple disks with the controller. So disk, track, sector, and DMA base address. So those are the values we want to handle. We have read and write strobes, which are going to be dealing with all sorts of weirdness. State information. So 1, 2, 3, 4, 5, 6. We will have a whole bunch of internal states added later. So dev init, we give it a name. Dev linked. I'm going to have it be dev close because we may want to write data back to a disk file. There's two ways of doing this. First off, I can, whenever a write operation is done, I can initiate the write at that point. I'm beginning to like the idea of a background thing that services this. And yeah, okay, we'll have a service thread that actually does the reads and writes. We are not going to connect to the network. And I'll work. The thread is going to have some internal state to work out what's going on. That means that I probably want a data CTRL and a data status. So when somebody writes control information to us, we can put it in CTRL, and people can update status as time goes by. There. Now, within the simulation, all we're going to be doing is just writing control, reading status. It'll be up to the thread to pick up that information and do the work and update the status and so on. Okay. So, let's start by just hooking things up so that it accepts the data. So we still have a main. We're going to have a bunch of stuff that we do. Okay, so control and status. Oops. Right, 0. So what can I say about pthread t? How can I have a pthread t that is nothing? It is an opaque type. So pthread create takes a pthread t. I think it's supposed to be completely opaque. Okay, so X11 does some threads. Thread DB. Oh, this is uses pthread t to define stuff. So GNU pthread types says pthread t is a unsigned long int. Thread identifier. The structure of the attribute type is not exposed on purpose. Oh boy. It is an unsigned long. Can it ever be 0? Probably. I can't count on it. I have to treat it as totally opaque. So, of course, none of this is compiling yet. Okay, so let's go back to bdev.h. So coming down from the top, let's do a those are all data things we want to initialize. Okay, and edges. Let's do the edge inits here. Oh, that doesn't have a slash in front of it. Okay, so now we say that and lowercase it. No, we need to uppercase it still. So we have control read and write, stat read and write, DMAH read and write, DMALR read and write, disk read write, track read write, sector read write as our names for those 6 guys. Then we set data to null. Okay. So I have to know whether the thread is still alive or not. So we're going to toss his storage out there. We're not going to expose what it is in this header file this time. But we do need to have one of these. Actually, I'm going to tuck the thread in here. And this is a pbdev. So now we are looking for, if we have a CTX pointer, then we're going to dive through it and shut things down. Now, if the service thread itself wants to go away, oh, I still need to join. Need that in the parent so I can still join up. So if the thread decides to die, it can clear itself out and null out the CTX. I need to pause and think. I need to also hit the bio break. I'll be right back. Okay. After a moment of thought, I am dumping the BDEV SRV stuff as being completely unnecessary. I will need to have some information here. We just say int thread state. Okay, I have init for not yet started. We have run and we have stop. So we're going to start it in state 0. If we create the thread, we're going to go to state 1. And if the thread decides to die, it can go to state 2. If it goes to 2, then we need to do a join. Now, on our side, we can set it to do and do a join, which means the thread is going to need to watch for that going to stop and hold it down. So stop will tell both sides that we want to shut things down. So what close is going to do is it's going to say if d arrow thread state is not equal to bdev state init, we're set to stop. We're going to pthread join the thread, and then we're going to set the init this back to init because now we are basically back in the initial state with no service thread. Okay, bdev invar, yay invar. We can map this basically on all of these guys. There we go. bdev linked. We now need to go through and hook all these guys up. So all we're doing is we're just going to hook those up to read and write from these data words. And it'll be up to somebody else, the thread, for instance, which is monitoring these guys to wake up and say, oh, I have work. And this isn't going to work because I don't have access to data from here. That's the problem with only having one parameter. Macro time. So I leave that off the end. That means I've got the name and arguments. This is the signature for the read function. And then we say decal read of reg is equal to static void sig rd reg. And impl is data 2 of d arrow reg is val d arrow data. Oops. And the trailing one, as with before, so we can have a semicolon after it. We've got the static in two places. STAT, DMAH, DMAL, DSK, TRK, SEC. And the right is like that. So we're actually going to need to have declarations at the top of the file. So let's put this whole thing up here. edge init has a final initial value, which we're going to set to 1 because these are active low. So that gets us down to this con thing, which we don't have. And then we've got a service thing, which is completely different. So additional thing I want to do maybe is if somebody sends a control word, maybe I want the status word to immediately go busy. And one way we can implement that is with somebody listening to control that reaches around and sets status to busy. So we'll immediately go busy, even if we're not seen here. Yeah, because we can't read back the control register. So there's the other thing, is that we don't have control and status separate things. Yeah, okay, I goofed up. Control and status are the same register. Control is only written, and status is only read. Oh, joy. Let's check the invariance first. Now all of this stuff actually goes up in bdev invar. And it's already there. So let's go back up to the top and do a quick review. We are defining the functions that will store and retrieve data from our various registers. We have this. So we are initializing all of our registers and all of our control signals. And we're grouping them up so we can see what goes with what. Thread state is init. During close, if we're not init, then we're going to stop. We're going to wait for the thread to be done and set it back to init. The invariants are thus. We don't require a thread to be present for our invariants to pass. If somebody tells us they have linked us all up, then then we can go ahead and set this. Actually, we can set these functions up here. No, we can't, because those functions access through dev, which may be unset. Right. We don't want them to be present while data is null, so we check that data is present and proper before we redirect. Now there's implementations, which do read the data value and stuff it in the register, or read the register value and stuff it in the data. Now if we go data valid, D arrow, so the control register gets a update. bdev go busy. So our control values, this really belongs up in a comment at file scope. Now, I guess this means that we could, yeah. So if somebody writes a 1, we initiate a read. If they write a 2, we initiate a write. The thread will put back in idle or busy for its own bookkeeping, but we won't be doing that. So inside the thread, we may be doing other things. Okay, so there's our status bytes. This is the A drive. How high do I want to go? How many disks do I want to support? Support drives C, D, E, F, G, H, I, J, K, L, M, N, O, P. I think that's B16. Yeah. Let's support, allow drives A through Z. And I'm going to actually use the drive letter as the disk value. Commands are ignored immediately complete if the if DSK value is out of range. Okay, track. We're going to allow all tracks. So I believe sector starts at 1 in CPM because it starts that way in some controllers. C has a current track number. Sector. Yeah, so 1 is the first sector. So sector numbers start at 1 on all the old disk controllers. So we'll allow sectors 1 through 255. It's kind of weak. How about track number? Yeah, track number starts at 0. Disk number 0 through. Yeah. Okay, going to have to match normal behavior So for computation of the address of the offset into a file containing the image of a floppy disk, we need to know how many sectors per track for that floppy disk. And I am pretty sure this is all over the interface guide. Although maybe not. Maybe this isn't, that's not the document where I saw it. There's a document on modification of CPM, which gave me the CBIOS stuff. Do a little more in-depth searching here. Yeah, there's a somewhat larger manual on CPM, which includes this table. So for the diskettes containing CPM itself, it is assumed that track 0 goes up through sector 26, and then we start reading from sector 1. So we need at least this many. And this means that any images I get of disks, if there's just a binary image, it is quite likely that they have 26 sectors per track. One sector follows track. So do we want to have a configuration thing here? I mean, a real disk controller would just drop the head onto the magnetic medium and it would look for sector number 22, and either it finds it or it doesn't. Likewise, if you're seeking out track, eventually you're going to seek off the end of the disk, clatter, or seek to 0, where either you're going to get a limit switch going, or you're going to go clatter, like the Apple II was famous for. It's a friendly little sound. Anyway, so when we load up a file containing an image of a disk, I think the same thing that says mount this file as this disk is going to have to tell things like how many sectors per track and how many tracks are on the disk. Also, later on, I believe that CPM 2.2 started natively supporting interleave. Although I think they did something weird. There was some sort of indirection table that it had. Not important, but we may model that if we do model timing. Okay. So bdev go busy. Byte CTRL is equal to D arrow CTRL arrow value. So if we have a non-zero value in control, what I'm going to do is data to D arrow stat So I'll have a NOP value that I'm going to define for the control byte. So here, if anybody updates the control byte, we're going to call this function, which will say, oh, what's the value? If the value is not NOP, then immediately set the busy stuff so that the thread, when it gets to work, can pick up on it. But if it doesn't get to work in time, the code looking at the controller won't immediately read control back and say, oh, it's not busy anymore. It must be done. Okay. That's got that. To do, see if the command is present. To do, execute the command. To do, clear the set status. So see if we ought to terminate. Let's leave to-dos in here until we get this compiling. To do set. Oh. Only if a command is present do we want to set status to done. There's a danger here. If we set the status to done outside of this, we could very well execute a command. And then we could set the status to done at just exactly the wrong time. So let's do that inside that thing. So if a command wasn't present, pause for a brief time. So we still need a way to, thread state is how we're mirroring that back. I'm going to put that in the header file, even though it's only used in this source file, just so I have it on hand. So at the top, we're going to say if, how about while, this is going to be a bdev, let's see, I can do, no, I settled before on doing the void, so p bdev is equal to p bdev a. Okay, so every time we're on the loop, we're going to check our state. And if it's state run, then we're going to do stuff. Otherwise, we're done. Okay, so now we're going to say EFD arrow CTRL. Oh, actually, we're going to do byte. Okay, it would be better to go away until someone poked CTRL, maybe someday. So the idea there would be when somebody pokes CTRL, we would have the main thread then notify this thread that it should run. The other way to do this is to actually execute the service inside poking CTRL. Not a bad idea. Better yet, inside stat. So we can carry our state and we can do all the work inside reading of the status word. So I've got too many lines here. Impl write needs to write status and all this stuff. And this needs to read control. And this is read status. Now the interesting thing is that reading of status is going to be very, very special. I'm going to do all the work and read status. Oh, no more thread, no more thread. Yeah. So each time we read status, I am going to do something for the state machine. There. No more thread, no more thread state. We're not going to do any thread state. We're not going to have a close. So pdev read control declared static but never defined. So here we want a read control. Haha. Yes. Read control doesn't exist. And write status doesn't exist. Bdev service doesn't exist. pthread main doesn't exist. pthread is no longer needed. syssocket isn't needed. inet isn't needed. Boom. So I'm going to do all my work inside the status gathering guy who is going to look at the TOWs and decide what to do. The actual work of the mass storage unit is performed bit by bit, little by little, each time the host, the simulation CPU reads from the status register. Is performed, how about as the simulated? So in theory, we could perform the entire operation the first time somebody called stat, and we could return the thing. This also means we don't actually have a stat register per se. We do have a signal, and we do have a control. Oh, no, we do have a stat register. I'm sorry, we don't have a control register. Duh. We no longer have data go busy because that's going to be part of our state machine. That does simplify things, doesn't it? Decl W, we no longer have a control. Right. It's the control register that doesn't exist. Control register exists because we need to be able to write to it and have it retained until somebody says, hey, are you done? When they read the status register, we'll then decide how much we've gotten done since that was written. It also means that when we write the control register, it's not actually a data item, is it? There. So we don't actually have stat. We have control read and status write, which will do work. We will have some information we carry about what we're supposed to be doing and when. Okay. So let's see here. With the right to control, we need to store information about what operation we're doing. And when we read from status, we want to be able to determine if the operation is completed or not, make any state updates to memory. Yeah, so I think during write, what we're going to do is we're going to write garbage to the DMA destination. Okay. And possibly snapshot the DMA source. And then during the other end, we can verify it. So if anybody reads or writes to the area that we're DMAing to or from during that period, we're in trouble. Generally you are. You don't want to mess around with DMA buffers while the device is moving from or to. Yeah, see what I'm doing now is I'm bringing everything in synchronously into the main simulation line. Okay, so first off, let's just do that. So we will report any commands and we will simply say we're idle. So let's get that working, and then we'll start hooking up commands that actually do something. So I need to implement bdevbist now. So what would I want to do out of a command line test to test a block device? I don't know if I want that yet. So let's just write bdevbist straight up. So it's not, it needs data, needs a name. We will be defining all of those things. Let's set up some names for the edges. Does that look right? Okay, now we need to, I think we're going to need these guys as well. Okay, so that gets us some locals that we can use. Bunch of defines and not used. Hold on. bdev test cdev. There we go. Yeah, you do not want to have name collisions even with static data. The only time that would work would be if you were, if one of them was a file in a library somewhere where you stripped out the local symbols, because otherwise, debuggers get very confused. Okay, so there's bdev test. Now test main.c. We need to have bdev. Oops. Don't have a benchmark for this. Okay, and we're getting into the test. So we initialize our data word, our data bus. We set its value to 0. We initialize our device. We say, we've linked you up. Then we have all these things we can do. What I want to do is for each register, I want to write FF and then 00 to it. And I want to test it. And I want to do that for everything but control and status. So leave control and status for the end. Oh, let's do this as a macro. So our test sequence is going to be data arrow value is equal to 0xff. Actually, plus tau. Actually, for a valid test, what we really want to do is write to each one. So I'm going to write a macro that says how to write a value to a register and how to read a value from a register. Use 5.5 as my, you didn't write a value error marker. So we're going to say DMH, RD, and we're going to say B is equal to data arrow value. Okay, so there's my macros that I will use for manipulating this thing. So I'm going to write a value to each register that is different. So let's see. Let's start with the bottom sec. Let's write 26 to the sector. Track. How about track 36? Disk. Let's write to disk 3, so the C drive. Actually, that's the drive. DMA L is 128. And I'm going to put this in the wrong place. So it'd be 0280. do those. Then let's do it again with a different value. So sector 1, track 0, A drive. Actually, let's put this at 0232. DMA at 0128. Okay, so that has exercised each one of those registers as separate storage. And where I have DMAH underscore, this needs to be reg paste underscore. So I'm not actually using these values yet. The other thing I can do is I can insert these guys. So assert. Let's do it looking at the register itself. Same thing down here. So we're asserting that we can write to it, that we get the right value in the register, and that we can read it back. Test condition failed. Sec value is not set to 26 at this point. It is in fact 0. Let's copy these up here so we can get an earlier failure on just the first one. Okay. So on falling edge, these guys. So I am doing a falling edge on the sec one, which is this guy here, sec read. So sub 5, so this should be going to bdev read sec. Oh, just looking at it, I can tell what's wrong with it. You can tell what's wrong with it too, can't you? So the write was moving from register to data. Wrong. Had those just exactly reversed. And we're much better now. So now we can write and read our register contents. So we got status being reported. Okay, so we are getting into the function with the proper values. Okay. So eventually I would like to actually simulate the timing, which means saying, well, it takes a certain amount of time to step for each track you want to step, and it takes a certain amount of time to wait for the sector to come under the read head, and then we start writing data to memory at a certain rate, and then at a certain time we are complete. But that's not yet. What I am going to do, however, is I am going to put in here pending op. Here we're going to say D arrow pending okay. And here we are going to have something real simple. Int okay. So if we're already in the NOP state, so if our pending op is nothing, we're done. Actually, no, that would allow somebody to override. So requested op in current state. So this guy can always set requested hop. Now when we're in the idle state, we look at pending op. We set stat appropriately and return our stuff. So the control, this means next time we call read of stat, we're going to execute a state read. That's fine. Now, once we've done this, I can set pending op equal to edev control knob. So that resets that word so we don't continually execute the same command over and over again. Except it's not pending, it's requested. So for idle, we're going to shift state. On the next read from the status register, if we're in the RD state or the WR state, we start to do things. Current state and tau. Let's not do the fancy stuff yet. We're getting a little bit fancy already. I do want to have this forced to return busy once. And that does that. And now this says we're going to actually just do the read. DSK value plus A. Okay, so we are receiving command 00. status 00 reported. Receive command 1. And we're reporting status FF. And we get back here because we started doing something. And currently we're just going to do that. Oh, wait a minute. Is that right? Yeah. So I should be using the macros here. So we get command 0, status 0 reported, command 1, status FF. Then we execute the read for that DMA address, status 00. Command 2, we execute the write and return. Okay. So for the actual operation, we'll do that. So we'll say we can go up to n times for some fairly large value of n, given that this is an actual piece of hardware out there. We know we're getting to BIST. We can turn that off. I don't need to do that or that. I will keep those. So we now have the simulation side of the device ready to go. Now we just need to hook it up to something that we can read and write. I'm going to need a disk image. Oh boy. We can start out with a disk image that is pure zeros of the appropriate size, and I can write a program which will format that disk, quote, format, unquote. In other words, a format program will create a zeroed image, and then we will have to write some code, write some utilities to write stuff onto it. But for now, what I want to do is provide a way to mount. Oh, and these decals need to be expanded. Whoops. Unmatched else. Okay, so let's Let's skip the indenting here for a moment. So way down at the bottom, what I wanted to extract were the actual lines here, because I figured that would be easier So I'm not sure why indent is having a hard time with this file on the right. So I want to direct my output to something, so indent bdev-e -o. So in the input file, there's that. So this is a unmatched else. Right there at the top of bdev init. Ho ho, it's inside this assert macro. So this assert macro is using some GCC fanciness that expands to some text that the indent program can't deal with. But I have my own uppercase assert that I can use instead, which takes some additional parameters. There we go. And now that indent's fine because the old indent program is too old to deal with the modern stuff from GCC. So this now expands to the way I like it. The GCC macro has to be more general because it has to allow assert in contexts that I don't handle well. Now, I actually, the way I wrote it, I force assert to only be used as a statement. There we go, all done. Now, I need some way for a simulation to say, hey, bdev, when somebody makes a request of you, I want you to fetch the data with this method. Now, potentially we have disk number, track number, sector number, and so on. I could farm that out to the simulation itself. So the simulation would have a function that, given the disk track sector, DMA high, DMA low, and whether it's a read or a write, it would then do the right thing. Do I want one of those per disk? No, what I'll do is I will do one of those, and then inside that we may implement multiple disks. How about that? We need I'm going to call this a BDEV impl, which is going to be provided by the specific implementation. And what it will have in it is it will have a hold on. I'm going to need to have information. So the other side is going to call into us and say, please call me back, and I'm going to want a wait a minute. How about void star impl ctx and void and impl fn there we have it. So we're just going to call back an impl function with impl context and a bdev pointer. The other end's going to have to do the casting for us, or it's going to cast it into this kind of a function, because I am just a little bit too tired to do all the dancing here. So if we're going to do this, then what I want to do is make this an if. So this is going to give us the chance. So we'll come in here at the top and we'll say, if we are idle, then do stuff. Roll it back, roll it back, roll it back. Or do we always want to force one? No, we don't want to do that. We want to get going immediately. So start off with, if the current state is idle, I'm going to do that. They're going to switch current state again, so that when we get into this, okay, we can then decide whether we're busy or not. So if current current state is idle, then we accept an op. Stat is going to start out as bdev state idle. So we're going to accept the op into current state. And we're going to come down here, and we're going to look at current state. And if current state is one of these guys, we're going to do it. Let's have an assertion that impl function is not null when we get into linked. Okay, so we need to pick us up here. Come on. Impl ctx is null, and impl fn is equal to null. In var, we're going to say so potentially each controller could use a separate impl function. We have one impl function for floppy disk, one for Winchester drive, one for whatever magic we want. So now if we run it, this is going to fail on this. Okay. So impl function is not set and we're failing. So now we can say impl underscore fn of what did I say it was? It was going to take the bdev and the ctx. So dev and the d arrow impl ctx. I'm going to set current state before calling impl function so he knows where we are. No, I'm not. So I am thinking that this could be down here. We don't need a stat, actually. Now, what's the difference between these two? Not a whole lot. So what I'm going to do is just turn this over to impl function here. Stat or state? State idle. And bdev stat idle is the stat value. Possibly confusing. So it will be the job of the impl function to take appropriate action based on the fact that somebody is reading the stat register. And I think actually I want to do this on the right as well. So this is seg5 bdev state step. So each time you write control or read stat, we're going to do a state step. Difference is here we set the requested op from data before doing it, and here we do it and then we set the data from the result. State says, oh, this bit of jiggery pokery we only really want to do in here when we write the control register. If we do that, that means if you write the control register while we're busy, we just ignore it, and that's what I want to do. And that means that the common code is really just these two lines. So there's no point in having an extra function. So, error there if requested op is not recognized. Error there if we have a requested op and we're not idle. So if we're not idle, implement. Then down here we say if we're idle, else report busy. Okay. So in the test, when we're setting up, we do want to provide an implementation function. And we do want to link it up here. Oh, I forgot to do that. Okay, so we need to have some way of saying, set the impl. So extern void bdev set impl. So as usual, I'm providing a macro to allow the caller to specify things that are of similar but not exact types and have it do the right thing. So now before we do bdev linked, we need to do bdev set impl of d bdev bist impl, and it's going to take a context, which is going to be null for the moment. Now, what we want to do when we get here is simply claim that we've done the right thing. I would like to print out some stuff, but let's just claim we've done the right thing for now. Okay, so we're getting there somehow. So we called into the function did I write bdev set impl? I did not write the bdev set impl function. How about that? Okay, here's a case where I do need to set the type in the indent profile. I know, picky, 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 but there it is. So now we're getting to here. Russet op not recognized. So I'm going to put in a special case, bdev ctrl nop break. Explicitly set the state to state idle. These two actually do nothing. Hello test bdev, we're getting here. and we're saying read, and we're getting the first failure here because it's coming up done on the first call, and the test still does the wrong thing. There we go. So this is going to give us up to 1,000 polls of the status word to come back with the idle. And now we could, in theory, use our private state here to extend what's going on in here. I think what I am going to do is have some private state. So what I want for my private state for the state machine is I'm going to have a notion of, for each disk I have in the array, I'm going to keep track of where it is and what it's doing. And actually, no, I will have a current for each one. I'll have a current state. And then I will stepwise change state from one to the next. So byte. We have a currently selected disk, currently selected track, and a sector that we're about to read. And what I'm going to do is assume we can write 1 byte per tau. So tau busy until. So now, this guy needs to be a bdev ctx. So if we haven't reached busy until, we're going to return. This also means we need an init static void bdev CTX. No, we're just going to do it in one place. I'm just going to call it CTX. So I think what I'm going to do is I am going to say when we switch to a disk, it's completely unknown state. So we have a ID of seek pending. So what will happen is that if need track 0 is set, we're going to seek all the way to track 0, and then we're going to seek out to the proper track. So we're starting to build a model of how a floppy disk drive actually works. The difference is that the real controller would probably remember the head positioning information for the various guys. Current sector isn't a thing. We're going to compute what the current sector is based on the disk. Diskettes rotate at 600 RPM. Let's see. So 18 million iterations. Okay, this is actually easy to do in my head, which is equals to 10 RP revolutions per second. So we're advancing at 260 sectors. So 18 million iterations of tau per second divided by 260 of those per, this means so it's 128 bytes. Let's assume that there's, let's do it 160. Let's round these numbers a bit. So instead of 69 tau per sector, I'm going to run my disks a little bit faster. This gives us 2520. So that would be 19 tau per byte. Let's round that down. Assume then move data at 16 tau per byte. Leaving time for hidden overhead. Data start mark, sector number, and 28 bytes of data. Checksum. I am not sure it's there or not, but I'm assuming that there was a checksum. We'll just leave it there as if. We're not going to store that, so all we'll store is the 128 bytes of data. Now, I've worked out the math here. I'm not going to implement it right now, but what I am going to do is do a little bit of time. Now, seek times. Diskette drive seek time. Floppy. Put a floppy in here as well. Actually, let's do the 8-inch. So actually, it's 360 RPMs for the old 8-inch drives. Well, let's keep the timing that I've got there. We can always muck about with it later. Good grief. So everybody, of course, quotes average access times for floppy disk, and that was always very dependent upon the seek time. Oh, I'm seeing some pictures here of some old things that I had not seen in years. Wonder if I could get a pair of old SA800s at some point. Well, I'll tell you what. Let's just put those in as pound defines. The tau per sector of disk rotation is not constant for some Macs. So they had drives that they would spin faster on the inside, so you have a constant linear velocity, or roughly. Okay, so first of all, we would do tau per track for the seek time, and then we would load the head under the media, and then we would wait for the proper sector to appear, and then we would move the head, and at some point we would unload the head from the media. So if you were already on this correct sector, the unload did not happen, and the rest didn't happen. So 3 and 4. So you only unloaded the head if you were releasing the drive. Actually, I forget whether you had to load the head onto the media before you started doing the seek or not. I'll assume you do. So if the disk is wrong, we're going to have a delay while we select the correct disk. And once we select the correct disk, we have to run ourselves out until we hit track 0, and then we have to run back to the proper track. And once we get to the proper track, we then have to wait for the sector to come around, and then we have to move the data. And then we start moving the data. Now, without actually doing the proper amount of delay, so we're going to say if C arrow cur disk is not equal to D arrow DSK arrow value, we're going to assign it. And we're going to say C arrow busy till equal tau plus tau new drive. We also need to set need and we're going to assume we're on track 80. We're going to seek all the way out to track 0. So new drive is going to be, how many milliseconds do we want to wait for new drive? How about 1/10 of a second? I'm going to say 5 milliseconds for the seek time. Now this means that An 80 track seek is going to take a very long time. Let's do a 1 millisecond seek time at a hundredth of a second to change tau, because we're going to be sitting here looping in our simulation. Basically, yeah, we'll tweak those later. Okay, this is a very fast disk. We're going to wait 1 millisecond for each sector number. It has to go by. Okay, so if disk is different, we need a track 0. Then we say if C arrow need K0 amper C arrow. And I'm only gonna seek. Let's do 34 tracks. Now, when we do this, I probably should randomize my track number, but that's good enough. So the Apple II actually had no track 0 switch, so it just banged it into the stops for the appropriate number of times. I have literally forgotten. I think track 0 was the innermost track. So you could have smaller discs, and track 0 would still be the same center cylinder. Okay, so if current track is greater than, now when the tracks move, I am going to set the sector to something unknown. So cur disk. All these are -1 because they should be getting initialized as we move through our states. We'll see the disk changes and the rest of them go away. Cur track, cur sec, cur byte. And I'm paranoid, so I'm going to put my DMA just like that. No, I won't do that. Okay, so we end up with a number between 1 and 26 there. So we get down to here, we're moving. Anytime we change sectors, actually at the beginning of the command, we really need to latch latch current byte and current DMA into their proper state. The other one is I do need to honor whether I've actually got a command or not. So if the current state is equal to no op, no, not current state, excuse me. The command word comes in here, requested op. So current state is being set to read write, okay. So if we're idle, we're done. Otherwise, it's either read or write. So now, if we're going to go ahead and call the function even though our state is idle so that we can track that information here. So if current state is idle, then last state is current state, return. Otherwise, if last state changed and it's not, we're no longer idle, then we can say C arrow cur byte is equal to 0, C arrow cur DMA is equal to D arrow DMA H value shifted by 8, or DMA D arrow DMA H and DMA L value. And parens because C. So if the state changed, we're going to reset our byte counter and our DMA address like that. Then we start working with these guys. So switch the disk, switch the track, possibly seek to. So seek to higher track is seek out. Seek to lower track is seek in. We're going to remove all those prints later. Then we have a sector weight. Now when we start worry about when we start getting into the tau stuff seriously, we may need to go through several state transitions to move us forward. If somebody waits a long time, then calls status, maybe we did a whole bunch of these. Actually, let's put ourselves in a 4 like that. So we're going to go into a loop. So if we're idle, we're going to do that. If the state changes, then let's update tau so we know that our state is as of right now. But this, we may be moving forward. We want to continue back up here to the top of the loop. Now here, because our state changed at the current time, we're calling with a state change. We know busy until is the current tau. We won't be able to do anything else, so we can return from here. But once we start changing the state of the system, this may be called with a read sync later. We'll say, well, our tau is after busy until, so we may have switched to drive, so let's do that. And then we go back and evaluate again. In this case, we can drop down into the next test. No, we can't. We always have to go back and check tau. Recal seek in. And this is, again, a plus equals. We may be doing several seeks. if we get all the way down here, then we are past the time where we start moving data. Let's use 1 microsecond per byte. Now this presumes that our tower is running 18 megahertz. So when we get to here, we're at the correct sector. So now we can start moving the data bytes in. There we go. That should work. So for state read, we need to get data into B, put it out there, and then I'm going to print dname current DMA disk, track, sector, byte, and B. So we still have these to-dos for talking to memory and mass storage. Segfault, yay! Okay, pdev best edge 2, calling subs run, getting a null. And there's our source location. Because we're getting called with C of 0 here, because when I set it up, I said 0. Much better. Switch to drive C, and the test condition is going to fail there. So we do a whole bunch of recal seek-ins. Okay. Okay, so switch to drive A. We seek in a whole bunch of times. We found track 0. Track 0 is where we wanted to read, so we do a sector wait until we get to the right sector. And then we're reading sector 1, blah, blah, blah. And stat idle at 415,000. I think I am going to call it for the day. Let's implement the memory part of this, and then I'll call it. Because starting to deal with the actual files in the host file system is where things get a bit risky, and I want to be as fresh as possible for that. So we have our block device here. And we have our block device test here. And the test needs to know how to move stuff to and from data. I think bdev needs to know how to move things to and from memory. No, this is going to get tricky because I now have to implement DMA or I have to get myself a side channel which addresses memory properly. And I think I'm going to have to implement DMA hidden behind the curtain, so to speak. Essentially, when somebody does a sync, does a read from that I/O port, during that call, while we are reading the data, that's where this is going to trigger. And that's not a real DMA operation. I'm going to think about this offline. So we're going to call it here. We're going to leave this as it is. It may be what I will do is we will work with the decoder to say, please give us the pointer to the memory for this address. And we will get around through that. But that means that, registering address space for DMA wouldn't be subject to shadow. So this is something where we would want a side channel into the decoder for how we're decoding DMA addresses. And we're going to be doing DMA on a separate address data bus so that conceptually, we've got the CPU address and data buses over here. We've got our memories here. We're going to do a dual ported memory in our heads. In reality, what we're going to do is we're going to get a pointer to the destination and we're just going to shove it in. So, yeah. And we can take over that bus temporarily because we do have control and tau is not going to increment. Let's take a look at RAM real quickly. So if I were just to trigger the edges on the RAM, it would just go in here and data 2 of data or data from, just reads data here. So we can write to memory like this. Reading to memory, we potentially have the data 2 here causing problems. We might see a hazard, so we may need to look inside the data. So what we would need to do is reach through all of this and be able to say, allow someone to shove data in to the data bus here. And maybe that's just as simple as rewinding the when. Yeah, I think so. Okay, so that's where we're going to go. But we'll do that next time when I am nice and fresh and focused. And I will see you then. And until then, keep it small,